Today we do the third part, the last part of section A. We've done this. We are going to, today, I don't think I even put it in here. Today we're going to be looking at odd, even functions. And something called negative angle identities. Okay. And this is coming up when we get into section B. You see that in your notebook. Odd even functions, these are something that you may or may not have encountered in previous math classes. A function is an even function. Now remember, this is functional notation. Function f, when given a negative input, gives the same result as function f with a positive input. So what's a good example of that is y equals x squared. Whether I put in a negative 1 or positive 1, a negative 2 or a positive 2, the output's going to be just the same. I put in a negative 1, my output y, that's right, it's 1. Positive 1, I get 1. Put in negative 2, I get 4. Positive 2, I get 4. So if the sign of the input does not affect the output, you have an even function. You can recognize it graphically because it is symmetrical with regard to the y-axis. Just the same on this side as it is on this side. An odd function, if I put a negative input in, my result will be the same as if I had to put in a positive one, except the whole thing is negative. So a good example of that is y equals x to the third. The absolute value of the function is going to be the same. The difference is going to be here. So let's think about it. If I put a 1 in here, what do I get out? 1. If I put a negative 1 in here, what do I get out? Negative 1. So, oh, this one, the one I'm talking about actually looks like this rather than what I've diagrammed here. If I put in a 1, I get out a 1. If I put in a negative 1, I get out a negative 1. If I put in 2, I get 8. So that's that point right there. If I put in a negative 2, I get negative 8. So an odd function is symmetrical with regard to the origin. And it's characteristic, the sign of the input only changes, the only change you're going to see, the only change is the sign of the output. So we want to, of course, think about this in terms of trig functions. Which of these are even and which of these are odd? Remember the test for even, if it's symmetrical with regard to the y-axis? Well, this one is not, so that's not even. This one is not, that's not even, but look at this beautiful one. This is even. And this one is also even. If it's symmetrical with regard to the origin, it's odd. So up here, this one's odd, this one's odd, this one's odd, and this one's odd. Right? They are symmetrical with regard to the origin, but they are not symmetrical with regard to the y-axis. So we have two that are even. That's cosine and its reciprocal partner. And we have four that are odd. So for the trig functions, at least for the parent functions, they are either even or odd. And here's a little summary of that. Here are our even ones, two of them, and our odd ones. So where are the identities? Do we see them here? Sure do. We can say that the sine of negative theta is always equal to negative sine of positive theta. So for your odd functions, this will be true. For your even functions, it's even easier, right? Just these two. No matter if you put in a negative angle or a positive angle, they are equal to each other. So for the odd ones, you have this change going on. The sign is changing. And for the even ones, so simple, huh? Yeah, make that a smile. Using negative angle identities. Okay. So how might we use this? I've got cosecant of a negative angle. And what do I know about cosecant? Let's look back here. Cosecant, that's odd. Since cosecant is an odd function, we can say that this will be equal to this. So we can write an equivalent trigonometric expression using a positive angle. So this is positive. The function itself is negative, but the angle is positive. Now, just to practice using our fundamental identities, now that we've got the negative angles under control, how might this be transformed? We can use a quotient identity here. We know that cosine theta over sine theta is cotangent theta. So cosine squared theta over sine squared theta will be cotangent squared theta. So what did we use right here? We used a quotient identity. For this one, this is one of those where you're going to benefit by translating it into all sine and cosine. We already had sine here. How often this happens. This is a good strategy. Cosecant, the reciprocal identity, 1 over sine theta. Secant theta, its reciprocal identity. Then we distribute sine. We get sine over sine and sine over cosine, and of course sine over sine is just a fancy one, and sine over cosine again calls on this quotient identity to give us an answer of 1 plus tangent theta. Okay, back in class, you're going to be working on the homework exercise number 1. There's 20 identities there. I don't think you're going to knock those off in one class period. I'm going to give you some time to work on those. We'll do 2 or 3 days on that.